So the general topic is simulations. Okay. So we are used to primarily digital simulations today. When I was an undergraduate student, I had a course called simulation, but that was analog simulation. I do not remember any of that. Okay. I don't remember understanding any of that when I studied that book either, but some of you managed to go through that course. That was analog simulation. I just haven't bothered to go back and check up into it. This is with the old devices, op amps and things like that, right? W folks might remember better. The Rajaraman's book was there. We went through that, mechanically, but I don't recollect at what that simulation meant even today. So we'll ignore that. So we are talking about digital simulations, right? So in that there are essentially mainly two categories, right? So you have so-called static simulations, where there is no time axis. Then you have dynamic simulations, where there is a notion of a time axis, and it's we also refer to that as discrete event simulation. So a static simulation system is usually used with random number generators, right, for some sort of combinatorial probabilistic analysis, right. So for example, what we did in our emulator is basically the static simulation, right. There is no notion of time. You are simply right flipping coins, and then you are saying I am starting in state S naught or as initial state Si. Then there is some probability of going from one state to another state and so on, right. So you are essentially simply moving from state to state, but there is no real time axis as such. You are simply repeating the experiment umpteen times and transitioning to the various states to understand the behavior of the system. And then from that we said, okay, I spent so much time in state S0, so much time in S1, therefore average of that gives me the probability of being in each of those states, right. So there is no real notion of time, it is simply random number generation based modeling of a system behavior. So that is what right, that is easier to do. That is also called your right Monte Carlo simulations. So we have this birthday paradox, right. You remember the birthday paradox? What is the probability that two people right in a room will have the same birthday, right. So that we can do mathematically, but how do I validate that? So I can validate that by simply right generating random numbers for every person's birthday, and then right looking at just have say 100 samples, randomly generate a birthday for each of them. It will be 1 over 365, right, uniformly, and then simply fill up say 100 such birth dates, and then calculate the probability. Okay, what is the probability at least one pair will have the same birthday? So that is done by simply right looking at all possible combinations, and of course I can run it for 100 users, 1000 users, million users and so on, and then I can also try this number of trials also. I can do just 10 trials and come up with a number, or do 1000 trials and come up with another number and so on, right. So that is essentially a static set of simulations. In the other context of discrete event simulation, which some of you already have done WCN, right, some of you have done NS2, so should how many of you do not really know the fundamentals of NS or discrete event simulation? Alright, so most of you seem to know what discrete is. Okay, then I will turn the tables around. So tell me, what is DES? Why should I bother? And then we will let them also, they will listen and I will pitch in, right. So what is a discrete event simulation? So we are now looking at modeling a system behavior, right, with time axis. There are some events happening with respect to time, there are some system changes, right, state changes that happen as time progresses in the system. And this is not only computer systems or networks or whatever it is, this is used everywhere, right. For our climate modeling also people try to do that. You come up with some, even for your prediction in terms of weather modeling for example, right, you look at okay what happens with time, here are some models for it, and then you introduce time in the picture and then see how that is, right, how the system will behave over long periods of time. Okay. So when you look at the system representation as such, why is it called a discrete event simulator?
We are not like taking it it's not fixed that such a thing will be happening. Like taking a random and every time it's a different value it's taking.
So first you represent the system state using some variables. So we need to first of all define system state, right? So that is the first, just like we did in the Markov models, right? You capture something as a system state. In the case of the MM1Q, when we used the Markov chain, the number of customers in the system was my system state, and I watched it. I simply model the behavior of that system state change with respect to time, right? So you have a system state which captures the state of the system in one or more variables. Okay. So if I have a multiple queue system, right, so for networks of queues, then the system state is basically number of customers in the first queue, second queue, third queue and so on. That is what is capturing the system state. Okay. So that is, so at an instant this is the state of the system. Now as time progresses, the state of the system changes. Okay. Now the state of the system actually will change on a continuous basis, right, literally. I mean, it's possible that it's, for example, if you look at the queuing system, at every instant of time the number of customers, one customer can arrive, one customer can depart and so on. So really it is a continuous, the state changes with respect to continuous time, but continuous time is hard to model in a real system. So what we do is we only look at the system state change at discrete events or discrete instants of time, right. So you say there is an event taking place, only when there are events occurring does the system state change. So you model the behavior of the system as a sequence of state changes where the changes occur at specific instants which we call as events. So some event takes place to change your system state. It is like interrupts in your PC, right. Interrupt arise, something is done, right. Everything is interrupt driven. If you look at a system, if the timer interrupt changes your process that is running on the CPU to some other process. If it is a hardware interrupt, you go and process that hardware. That will also invoke a change in terms of the system itself, right. So your state change happens at discrete right. So that is whenever an event takes place. So every event will trigger additional events if also in the future, right. As when an event occurs, you will be scheduling some other events in the future that that can handle something else and so on. So with this you start off your system with at least one event, one bootstrapping event that will then spawn other events as it gets. So every event will occur, that event has to get processed. So for every event you have to associate an event handling function, right. And so then the event handling function's job is to handle the event, whatever, do processing, and then in turn generate future events that will be again stored in some system, right. That is going to be stored and then that will be processed. So that is all. Your system now is simply a state of, is a sequence of time ordered events. So every event has a time associated with that, and you simply process the so called event queue in time. Okay. Yes.
Considering the events to be atomic, that we don't consider the state of the system while an event is occurring. We see at the beginning of the event and at the end of the event.
Yes, yeah. At the beginning of the event you will change the state and then you say okay, I am done. Then the next event is processed, right. So your system is, so essentially you have an event queue, right. So event queue is that tells you the set of future occurring events. At any point in time you may have some 20 events in the queue, right. So let us see if this is time axis, right. So there are events that occur at various points, E1, E2, okay. Now let us try to change the color. And let us say that the current time of the system is E4, right. So this is the next event that you are processing. You are processing event 4 that is taking place at some point in time, right, at T4, whatever that is. So then when you process E4, already there is an event E5 that is supposed to take place at some point in the future, that is already in the system. But as a result of processing, you might end up creating a couple of other events, E6 and E7, that occur in the future. So that's how your events keep on getting generated for future, right. So this is your that as a result of, for example, what is one event spawning another event. So if you look at the MM1 queue, right, event is server picks up the packet for service or customer for service. So when you pick up the packet for service, you will simply schedule an event that says current time plus service time, let us say 100 milliseconds, current time plus service time, I will schedule the packet completion event. So it is a packet transmission event. Essentially when you process that, you also schedule the packet completion event for some other point in time in the future, and the packet completion time might do again something else, right. But normally what you have is usually you have two separate processes. I will give an example of this MM1 system as we go along, but that is the basic idea. One event when handled can generate other events to model, and how is that generation done? That is where your logic comes in. You write the logic for generation of events, and where does your logic come from? Your logic comes from your understanding of the system itself, that is representing your system behavior, that is a model of the system itself as such, right. So then after E4 is done, then you will say process E5. So then the system moves on to processing E5, right, and usually you do not try to schedule events before the current time. In theory you could, right, because you are simply making an ordered list. You could say that E5 go and process something that happened before E5. That is not what we normally do, but I can certainly do something like this, right. I can create E8 which is ahead of E6 and E7, right, some other event that is supposed to be processed before E6 and E7. No, every time you have to create some events. You are, as part of your logic, you will say this, you start off with say only one event. Event is, let us say, the first arrival in the system, okay, and then the first arrival in the system when processed will spawn the next arrival in the system, and so on. Okay.
Place I will move to S2. So I am just changing the states.
But in between there may be other events that can take place.
But still, sir, with prior knowledge I know all these states.
No. The states is not the issue. Well, I will show that example, right. Each of your events, there are several possible events that can happen, right. Only thing we are doing is time ordering, but you will not know you might know all possible states, but when those events are going to take place is going to be a random time, right. It's a random generation involved there.
New packet is coming for arrival, so this will come at the same time. We were working on the departure, at the same time when the arrival
can be coming in. Yes. Okay. No, that will not happen. That's why we will have to see. Let's look at some examples. I think then this will be clearer.
We can use the events that are already generated but ahead of in time.
To generate it, you will generate an event when you are processing an event.
Suppose now we are processing E5.
Yes.
And generating new event. So
E8,
can I use E6 and E7 in the
No,
logic?
E6 and E7, no, you do not know. No, they are simply sitting in the queue. That's all. They are supposed to happen at that point in time. But E5 processing cannot. You can, if you know the existence of, you can delete that event, but right, and you can delete some future events. For example, timeouts in a packet transmission, right, in a link. You will schedule a timeout interval, a timeout event always every time you send a packet. If you get the acknowledgement and you know when this particular event is going to occur, you can delete that event. That you can do, because that is what we do in our real life too, right? You always cancel the timer.
If we know the time of the event exactly, then
yes.
we can use it.
If you have a handle for that, there is a time or some handle for that. Usually every event you will be given an event handler, or some pointer will be there, right? Some sort of representation will be there for you to handle. So you can use that to do the processing if you want, but you cannot essentially trigger that event ahead of time. That event, if you want, you can reschedule that event to some earlier point. It's like essentially cancelling that event and then starting a new event ahead of time.
Sir, here even E2, E3, E4, E5 are like a scheduled one, and then E5.
So we start off with E1. Let's say that this is what happened. E1 is the first event in the system. We have to schedule the first event. E1 spawned E2. E1 processing took place. E1 spawned E2. Then E2 spawned E3, and then so on, right? So we are now at the stage where E4 is the current, E5 was already spawned by, say E3 spawns E4 and E5, right, with respect to time, and E4 is handling created these two events, and then the system says what is the next item in the queue. After handling E4, next item in the queue is E5, and E5 is basically spawning another event called E8, which is at this point in time. Okay.
So that is an independent event in the system, right?
Yes, that's an independent event.
So you can execute that as an independent event, then you can handle.
Which one? The E8.
E8.
For every event, you will have a corresponding handler. Whatever is handler will be invoked, right? So it's for like in signals in Unix system. For every signal, you have a corresponding handler. So here you will register for every event. You have to say what the handler code is going to be.
Can more than one event occur simultaneously?
It can. Then the system will have to do some sort of priority. Then you will end up with race conditions. If depending on which of those gets selected first, the behavior can change. Yes. So unless you have a way of distinguishing events like with a priority or something else, system can simply do first in first out. And if there are multiple events, it can randomly choose one and execute. So when you write your code, you have to be really careful about which one. If the order of execution of the events changes, which are scheduled for the same time, will it make a difference to your program? That is where sometimes errors happen. Okay. So debugging discrete event simulation code is always harder because of some of these unknowns, because there are randomness in the system, and the same pattern might not be repeated the next time you run the code. You run it once, your system will just hang. You run it again, suddenly it works beautifully. Why? Because this two events happening at the same time did not happen because of the way your random seed changed, right? Therefore a different set of random values were generated. Okay. So first now what we understand is the system can be modeled using a sequence of events. Each event changes the state of the system from whatever state, and each event can spawn other events. Every event has an event handler, right? This is what we have. So if you are going to write your own discrete event simulation package, okay. So now one more thing is that in this system there is a notion of a simulation clock. Okay. So the simulation clock also advances in discrete time intervals. It is not like a regular clock where you have to go from 0 to 0.1 or 0.01 and so on, right. So example, if this was at 0.1, right, this is 0.4, etc. So every time your simulation clock will be set to the current event time. So when you schedule an event, you will also tell what time that event is going to be handled, right. So your clock will jump from one event to the next event, and your simulation clock will start off with initially will be 0, right, and then when it handles the first event it becomes 0.1, the second event the clock becomes 0.4 and so on. So it is a discrete so that is how the simulation clock moves. So in every package you will find a simulation time, get simulation time or time now, right, that will be there to tell you the current time for whatever delay calculations and all those things. So that is how your system clock. Basically with these two things you have a discrete event simulation package, scheduling an event and handling that event, and a clock that is moving along with the based on the events that are being handled. Okay. So your typical simulation package so if you are trying to learn a simulation package, the first things you will ask for are these things, right. First is how do I schedule an event. And there are different ways to schedule events. The simplest thing is you schedule event 10 time units from now, that is all, in the future pretty much. Then if you look at this, the axioms are slightly more sophisticated ones. You can schedule based on a resource availability and all that, but the simplest is I am now at 0.8 time units, schedule an event for 1.2 time units, that is all, right. So that is the event scheduler. And then also how to cancel events, right. cancelling events, etc., right, creation, deletion, modification, rescheduling, there are lots of variations, but the simplest thing is create an event, and then you also have to how to the event handling routines. So event handling routine is basically your core logic for the program that you have to write, but you have to know how to associate each event with the corresponding event handler. So for example in Yaxem, right, you have something called new event, you will give it some name, right, event 1, some string, this is mostly for debugging purposes, then you will say arrival process, right, say arrival is simply a name of the function pointer, it points to a function called arrival which you have to define somewhere else in your code, and some other things, right, and then you will also say the time into the future, right. Now this will be simply the event creation itself, then you will have scheduled event, right, for example. So this is defining the event, you might have some pointer e equals to this, right, and then you would have something like scheduled event. Scheduled event is not in Yaxem, but is approximately what we will say. So scheduled event e at 1.5 blah 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 something. So it is relative time, it will tell you whether the syntax is relative time, absolute time, but it is always, that from now, for example, you are scheduling a packet for transmission, right, you know the length of the packet, so you know the time it is going to take to complete the packet, so simply comma the service time, right, that is going to the time into the future, you will schedule the completion event when you start the packet. So that is a first and then this notion of, right, simulation clock. Because all your delay calculations depend upon this clock interface that they give you, right, plus the time advancing mechanism. Then how do you represent state variables? If it is C, then it is a bunch of C data structures structs. So there is nothing there. The rest of this is about it, right? There are lots of other things listed. How do you get like all the input stuff, right? Okay. So then in addition to this, what you would need is some sort of statistical interface, right, okay, some statistical functions. These are not compulsory, but most of the times because you do not want to always keep on calculating the mean and standard deviation and all that, system can simply do that for you, right. So every time you say finish a packet transmission, you know what the transmission delay was, you simply want to say here add this to the some statistical variable that you create, you simply say dump it on this variable, let that take care of getting histograms or means or whatever it is, right. So the statistical functions, if they are there, it makes your life easier, so you have to look for what are the different statistical functions, okay. So in the case of Yaxem there is something called statrec, so from the statrec you can get lot of so there is a statistical record is a function or it is a variable, and for this variable there are a lot of functions that let you get the histograms, mean and all those things, right, and there are sophisticated ways of actually computing this means, the point means or other things. Then it should also give you trace and debugging, right, routines. This is particularly important because it is not sequential code, right, there is a lot of time randomness inherent there, and sometimes we will see if it is it can also be essentially just parallel code, right, within the same simulator I can actually have, just like a Unix system, I can have multiple processes running, and then those processes, just like Unix process, can share variables, can have semaphores, right, barriers, all those things are there in system like Yaxem, others might not have, but you can also essentially write your code as a sequence of interacting processes or as a set of interacting processes, and then you will have to worry about all the synchronization constructs, so which is also typically available, so we will list that also. right, synchronization constants. And then one very important thing, I am sorry,
Graphs.
graphing. Okay, your statistical packages, yeah, some of the packages give you graphing utilities, but if you look at NS2 gives you, well, there is NAM for example, right. Sometimes they have animation, right, because if you simply run a simulator and then look at the numbers, one lousy trace file comes out which you have to sit and process, right. So there are maybe some, okay fine, we will say, right, output visualization, animation, right. So when Shastra comes, you are asked to do a demo, you simply get OpNet and then use OpNets, right. So you can run OpNet, show as we developed OpNet, and then show them in simulation of vehicles moving around and all the demonstration. So but it's fancy things, but that is usually only for useful only for this demo purposes. No, besides that there is still one very important documentation. Okay, documentation is fine. Documentation, there is one PDF file, that is about all that you will see for documentation, and some example files that are there which I wrote some time ago. One very important thing, all the, yeah, how, okay, so we are talking, okay, that is a good point. When do you start and when do you stop? Usually packages do not tell you that, you have to implement your own routines for example, right, because your system will always start in a transient state and then it reaches steady state, okay, and later on we will see how do you know the system has passed the transient state. Sometimes people want to analyze only the transient state behavior because that is very important, sometimes you only want to analyze steady state behavior. So you have to have some ways of specifying transient versus steady state, which I am not sure if all packages, right, let you do that because it is so dependent upon the variables you are trying to monitor. Like some variable might reach steady state quickly, but some variable might take steady state might take a very long time depending on what that you are measuring, right. Transient versus steady state, right, detection, because there are two things, you initial data in a simulator will always be not useful for if you are looking at steady state results, and when do you know when to stop the simulation, that also package will never tell you. In fact this package Yaxem does not, but there is some extensions that you will see called new StatRec and so on which will try to do batch replications, and then automatically let us say you are trying to converge on delay, so it keeps for every 500 customers computes the delay and so on, and then finally you find that there is no point running the simulation any longer because delay is now more or less stabilized, right. So if you look at your system behavior, let us say delay is what your average delay, right, is what you are trying to plot with respect to time. So first customer delay will be something, then your delay will kind of go up and down like this, but finally at some point in time your delay values, because this is a long term averages, right, so will finally stabilize. And if this is a steady state, then you want to know that, right, beyond a point running the simulation for another 2 hours will not make a difference, so when do I stop my simulation. Many times people simply say 10,000 run whatever 5 minutes of simulation time, right, man at NS2, whether the system steady state is achieved or not we do not really care, 5 minutes because it takes 2 hours or I cannot run any longer, so therefore that is the end of my patience is over, right, this is the numbers, take it or leave it. And sometimes you are very keen on, right, how long does it take to reach steady state for example, or what, because queue behaviors change, right, during this, if you are studying queue oscillations for example, the study in transient state might be more useful. No, I am still looking for one more very important thing. So sometimes packages might give you ways of automatically, right, there is auto terminate, you will see that function in Yaxem which will say auto terminate, and it will work only if the system will reach stable condition. If the system, if the particular variable looking for does not really converge, then the program will run forever unless you give some upper limit on time. One very important package is missing. We are talking of time, we are talking of discrete event simulation, right. You need random number generators, right. You need random number generators, not just uniform. How do you generate a random number in Linux or Windows? You have random or LRandom, right? So you have some RNGs in the system, okay. And if you want double values, if you want double, random is integer, right? If you want double, drand, or you also go to MATLAB for what? You didn't say, okay. So you need some very good random number generator, right? This book has a chapter on RNGs, which let's say there are two. One is mathematically you should prove that this is really got right randomness properties and the cycle is very long and things like that. Then there are cryptographic random number generators, but generally you need a good random number generator, not just for uniform random. What if I want to generate exponential? How do I do that? I want to generate an exponential random variable. I want to generate a Gaussian random variable, right? I want to emulate Poisson arrivals. How do you do that? You've done RNGs?
Take the inverse of the function you want and you will get the
yes.
probability.
So that is one of the ways. If inverse is not readily available, then you will have to go for other techniques, right? So usually we can do this ourselves. If I simply give you a uniform random number from 0 to 1, I can translate that into an exponential random number generator, right? If the inverse is easily figurable, but in some cases inverse is not available. So again there is a chapter on how to generate random variates, which we will not get into right now. If you are really interested, you can look at that chapter, right, on how to generate random number variates. Exponential is easy because we know that the E of x we know, right? So because of the fact that E of x is, E of x not f of x. We know the CDF, right? So CDF is minus x, okay. Now what I want to do is, given mu, I want to generate a x which over the long run will basically emulate my this exponential variable, right. So what you will do is you will generate some y which is uniformly distributed from 0 to 1, and then you will essentially try to get your value for x, right. So given some number f of x, right, let us say r is the number that you randomly generate, you will feed it r into this one, then you will do your simple f inverse of x is what you will try to do, okay. So that if the system gives you these functions ready made, it is good, and then you can essentially start off with your random number generation, okay. And yeah, so these are some of the main entities that you look for internally. To actually, if I say build your own random numbers event simulation, discrete event simulation system, it won't take much time. All you have to do is be able to maintain an event queue, right. So how do you maintain an event queue? Simply an ordered list, linear time ordered list will do, but if your list gets very large, then your cost of maintaining that will be high, or you can use a heap, right. That's a heap is also possible, right, or you can have buckets, the so called calendar queues, where you have a set of queues and then sub queues, right. Again, I am not since that is not directly related to us, we are not really building systems, but there is a small section on how calendar queues can be used, and it is an indexed linear list. So this is these are all the things that you would essentially need, okay. So as a when you start writing your simulation model, right, so you figure out what are the system variables, and then how do you capture the logic of the system, and then two important things that which are not really sometimes available, which we mentioned before, is how to terminate the simulation and how to delete the initial data. It is called initial data deletion and terminating the simulations. So I will come back to that after the next set of classes, okay. So questions on this basics so far? So ready for writing MM1 code with the pseudo interfaces, right. What should, how would an MM1 system look like if I want to simulate an MM1 queue? What should the code look like? You will see the actual code on Wednesday, but you will understand the code better if you kind of see how the code will be developed, is being developed. So to develop a queue, or a model for a system, you first identify the entities of the system, right, and which is going to capture the state of your system and so on. So what are the entities in my system? What do I have to essentially build? I need a buffer, right, I need one buffer structure that will store, so I need some sort of, I need a buffer, and this is a simple FIFO buffer, right. I can make this more complicated if I want to, but let us say it is a FIFO buffer, so that you can write in no time, right. Simple linear linked list will do, or doubly linked list, whatever it is, you are adding elements to the list, or queue basically, right. If you, unless doubly linked list, if you want to do something like priority based scheduling, right, where you do not maintain the list in order, if you randomly, or you do random scheduling, but queue structure will itself do, right. How do you can write a queue to add elements at the end of the queue and delete elements from the beginning of the queue, so that I can. Then how do I, then what else, I need also to emulate the, I need to have something like a server, right. I need the server, I need something to emulate the behavior or to model the behavior of the server, where whenever the queue is empty, the server will go to sleep, whenever the queue is non-empty, the server will pick a packet, then pretend to be busy for the duration of that time that it is servicing the packet, then, right. So you have to have some server entity that is going through the state changes, right. It is either idle or servicing, and as soon as it finishes servicing one customer, it looks at the queue, there is a queue, I can, right, go pick it up. Okay, so we need somehow to model that server itself. Then the next thing is, actually how do I fill up this buffer, right, how do I emulate my arrival process? How do I handle that? That will be Bernoulli, but here I am saying I want exponential. We can, what you did there in the first assignment, yes, you can say in every slot I will flip a coin and then decide whether it is a packet or not a packet, so that is Bernoulli is easy, but I am saying no, that is kind of simple, right. I really want to emulate exponential. Okay. So the way we do that is, so let us say that I have something called packet gen. This is a, let us say a process or some function that is going to be, this is when you start your system, you start saying implement, start with this packet gen. Okay. So I have to essentially simulate the first arrival, right. So what we do is inter arrival time, or let us say double. Okay. So we can say E equals, right, new event where this is some name for it, and let us say generate packet. The actual code will be slightly different because this is roughly what you can do, think of. So I am creating an event, right, just this only creation of the event, it is not scheduled yet. Now I want to schedule this event for the first time, so I use my schedule event, right, whatever is my sched event, right. So but before that I need to find out my inter arrival time. So I know lambda, let us say lambda is arrival rate, right, that is given to me. So I simply use, in the case of Yaxim, there happens to be one exponential generator. Since I know that my arrival process is Poisson and I know that the arrival rate, so arrival rate is given to you, so your lambda and mu are specified, that is about all that you need. In this is infinite case, buffer case, if you want I can do finite buffer also, no big deal, right. Infinite buffer changing to finite buffer is trivial. So I generate this inter arrival time, okay, and then what do I do, then I can simply say schedule event. So I will simply schedule this event E into the future inter arrival time. So right, so I have scheduled the first event. So from this instant I am generating the next event. then what happens at that time 0 plus whatever current time plus inter arrival, this gen packet is going to get invoked. So gen packet will simply generate a packet, some packet data structure you define, fill in the fields of the packet, add that to the queue, right. So fill in the fields of packet, add it to the queue, then gen packet will then essentially have to trigger itself again saying calculate the next inter arrival time. So this could be within a loop if you really want to do it, right, where you have a loop that will simply generate the packet, fill up the fields, right, and then you will reschedule the next event based on the next inter arrival time, right. So this is something that you would try to do. This whole thing you could put in a loop if you want to go back and forth, right. When you handle this the first event, you will generate the next packet's arrival, which will again be based on the same inter arrival time equals exponential by 1 by arrival rate. So you have this simple loop that keeps on repeating where you constantly generate packets. So this is a separate set of events that is happening. Packet generation is like one separate set of events that is happening on its own, it keeps on filling the buffer. On the other side you have to have the server that picks out the packet, right. So you have to have some mechanism now to have the server process to be scheduled, okay. So how do we do that with events? I have to have an event, but only thing I do not know when that event is going to get triggered, right, there is uncertainty in that event. So what will we do? With some sort of notification, or I simply create one event called server schedule at time 0 and we say server wake up every time instant. So simply reschedule that server, right, 1.0 queue empty, if not empty go back to sleep, or sorry, if not empty handle that customer, if it is empty go back to sleep, right, that is all. So there is this initial waiting period where you keep on checking whether the queue is available or not, right, whether there is a packet in the queue ready to be serviced or not. I can make that as my event. So I start with one event called server event, which is at the beginning of the simulation that initially checks every slot. I can make that unit even 0.01 slots because simulation clock does not really matter, right, I can do every 0.001 keep on waking up and checking. Let us see if we can write the pseudo code for that, right. So I have this in the beginning, right, in main I have created an event called say S. This is a server event and I have scheduled S to start off right away, server gets to work instantly as soon as the system simulation starts. So what you will do is you will normally look at a main program, will have a sequence of these scheduled events for all the bootstrapping events, then you will say driver run which will basically start the simulation. So you set up all the events, then you say start, right, you would have seen that in NS2 also, right, NS2 start and stop. So my server is now simply a function, normally it is void, right, function. Okay. Where you check the length of the queue, right. So if length of queue, right, equals 0, then in Yaxim there is a way of rescheduling an event without having to create the event again. You can simply say reschedule event at, so you will simply say reschedule with whatever granularity that you are going to wake up and check, 0.01 time units, check it again, right.
We can wake up the server, right?
Yeah, how?
The packet arriving event.
There is no server. Now my server is simply a function. You are thinking of server as a process, right? If there is a process, I can wake up the process. Here there is no process as such. There is simply an event function that is going to be triggered at regular events of time, right? There is also a notion of process in Yaxim, that will be next before I wrap up, okay. So this is one way of doing that. Without processes I can simply just have this event, else event of packet arrival can trigger, yes. So yeah, here what will happen is you are that no, actually there is no approximation. Whenever the packet is, yeah, there is this delay of 0.01, so there will be that will be off. It is not instantly that the server gets to work. That is if I implement it this way. I can also implement this with implementing the server as a process. Then I have synchronization variables in the case of, you can set up flags. So whenever a packet arrives or the queue length becomes greater than 0, there is a flag that you will set. Then Yaxim internally will go and wake up the process, okay, in the case of Yaxim. So there is a process model. I do not want to give too much, the process model examples will come, right. So if you implement as a process, then yes, you can do this. In fact, the example that you see you will see is using something called resource, which is there in Yaxim, which actually has a built-in server. So you simply take in an event and schedule it on a particular server. That is not as intricate as this one, but that is a starting point. A little bit harder to figure out what is going on because the implementation of the resource is within Yaxim itself. But if you want to really emulate a server, one is to do this kind of periodic checking for every packet, or have a process model, right. So in Yaxim you can also create a process. This is almost like our threads interface. Right, I will say P is a new process, and then you will have to schedule the process also initially. And you can schedule the process anytime you want, it could be 10 seconds, 100 seconds in the future, but let us say you want to start it at, right. So if this is what you do in main, then your server function is now a process that is always running in Yaxim. Now this server you can do your you can look for synchronization constructs, there is barriers, you can use semaphores if you want to, right. You have there, we can simply use a simple semaphore and just check whether the value is greater than 0, that is all. So you can use the same producer consumer construct, yes.
Reschedule if you give 0 on
it is 0.01 is what, yeah.
If you give 0, it will be running infinitely like a process.
Yeah, you do not want to do that. Or if you do that, then again what it will do, it will come back and check. But the thing is, if a packet, so what happens is, let us say that the same instant, so there are two events happening at the same time, one is a packet arrival and one is this checking. If the system that Yaxim scheduler picked up the arrival process before you, then you are lucky, yes. Then the packet will be there in the queue, then you will have length will be greater than 0, yeah. So that is there, yeah. You can also do it with that way, yeah. But for that, at some point that arrival process has to be selected. If the arrival process never gets selected, then that is all, that event will never take place and this event will be simply checking infinitely. So that is that catch that you have there, right. So now the server you can do time plus, normally it is time sorted, you can also have priorities for the processes. So if you want to say arrival process has high, in Yaxim at least there is a priority for the process. So you can say arrival process has higher priority than server process, because that way if there is an event, two events at the same time, you will schedule the higher priority process first, in which case arrival will be handled. So that if you do, then you will not have this race condition. This server will be an infinite while loop, yeah. So this will be while, just sit there, wait for a packet to arrive. When a packet arrives, you would, so in the case of a server, you will simply delay the server. There is something called process delay, like our sleep or right. So you pick up a packet, process delay, which process delay will simply put the process to sleep for one packet unit of time. Then when you wake up, you will update all the statistics that you want to do. Okay, so this is how it goes along. Update stats. So pick a packet, pretend to go to sleep, pretend to be busy basically, right. At the end of it, this process will be woken up, you compute the delay, whatever that you want, throughput all those metrics in the statistics, then go back and wait for the next packet to be serviced. That is also a model.
So going by that reschedule event, so if we put the time as 0, 0, like no but so that will stop time progression in the system, will it not? Because if we
until
if we consider the queue is empty at that point of time.
Yeah, so that is fine. Time progression will be stopped because there is no real thing happening. So it is almost like continuous time simulation.